and laundries, so that we can enjoy our lives while robots is doing these tedious and complex tasks. And nowadays, we do have lots of robots in industrial settings, as you can imagine, so such as car factories or warehouses. So these robots are extremely capable and accurate and successful at performing this level of tasks. So they can lift heavy objects beyond our human capabilities. They can assemble and transport things with higher than human speed and higher than human precisions. But meanwhile, we should also notice that these are kind of specialized machines working in specialized environments. And when we try to deploy similar algorithms in unstructured environments such as our homes, then the things get a little bit more trickier. So imagine you want to build a robot preparing breakfast for us. This is probably what will happen. And I'll let the video play. So the robot will make a sequence of mistakes while it's not going to correct these errors and just keep trying until it's pretend it's already a success. This video may be just a funny video I searched online, but this also highlights several, there are several limitations of current robotics methods that we'll try to bring them into our homes. Maybe just to name a few, we have noisy perceptions in the real world. Our planning algorithms may be imperfect, and maybe the physical world itself is such unpredictable world. But among all of them, so these are definitely exciting directions people work on. But among all of them, my research focuses on a particular challenge that I think is very fundamental, and without solving it, we can never achieve general purpose robots in our homes. And the challenge is, instead of using all these kind of specialized and effectors such as scrapers or suction cups, how can we give the robots the ability to use multi-finger hands and build robot dexterities? Which means we want our algorithm to be able to control and coordinate of multiple degree freedoms and manipulate objects in our desired way. And I think this challenge is very fundamental, and to illustrate why, let's walk through a very quick thought experiment. So maybe let's imagine today is not 2026, but after 5 years, it's already 2031. Then what might happen? So of course, by then, if you're a PhD student, you should have graduated. But another thing we can imagine is that given the rate of AI progress today, maybe by then we have already achieved a superhuman level AI, especially in the perception or planning perspective. Then what will happen on that day if we want to put these human level AI systems into robots we have today? And of course, we do not have such an AI system yet, but there are still something we can try to imagine. So here is the video that I try to directly control a pair of tongs. So the video is a little bit slow due to network, but I guess you can imagine. So in this case, I try to control this pair of tongs similar to a robotic gripper and try to perform a very simple task, just cutting this apple. So now the perception and planning are all human level because I myself control these parallel draw grippers. So I just use my own maximum reasoning capabilities to do that. But as you can see, it's not easy at all. Picking up the knife is very challenging, and then cutting the apple up even more challenging. I'm curious if I can directly share, because I think the Zoom video sharing is a bit laggy.
Yeah.
Is there a way to connect the?
Oh, the whole thing.
Oh, you did.
You can mute yourself and use these computers.
Oh, I think this laptop is still in the Zoom mode.
Okay, oh, yeah.
This is the video.
So if I do this, I think it's still quite lag behind. Yeah, but I think maybe that's fine. I think I can also later in the video later in this session, I can play it on my laptop so you can see.
Okay.
Yeah, but I think the point of this thought experiment is that even if we, like as a human, directly control these grippers instead of robots control these grippers, it's still quite hard to doing some daily tasks we can efficiently do. And on the other hand, we can, like if we use our hand, we can easily do this without any problems, even without thinking, because these tools are designed for our hands, and we use these tools every day. And in this case, we can very efficiently make decisions and executions. So I believe that if we ever want to build intelligent robots that coexist with us, work in our daily environments, and help us with the tasks that we are mostly interested in, they need to interact with the objects or tools that are designed for us, and therefore they must be equipped with multi-finger hands. And the algorithms try to adapt to that. And then with the goal of trying to develop such general purpose robots and can operate in our homes, so I spent my PhD doing some works trying to address this task. So during my PhD, I focused most of my time on the so-called sim-to-real approach for dexterous manipulations. And in this video, showing some of my work trying to do in-hand manipulation, and the video does not quite show it, but based on the left is showing you can in-hand manipulate some objects and showing the generalizations using one policy applying different objects. And in the middle, we can have apply same algorithms on two hands, trying to twist a bottle cap. And then on the right is trying to rotate pen-like objects using a multi-finger hand. And the for completeness, the idea of sim-to-real is that given the task, we are trying to build simulation environments. The simulation environments powered by current GPU-based rendering and GPU-based simulations. You can simulate tens of thousands of different robots working with different kinds of objects, and then you can optimize your algorithms with a lot of samples using reinforcement learning. And this is pretty good. After you find a way to train these algorithms, because it trained with huge amount of samples in simulation, it can be quite robust in the real world. So here are some policies that I released the code, and some people also adapt in their robot hand, and that can pretty efficiently just out of box. You can deploy the algorithms on different situations, such as this is from a colleague of University of Bristol, and also this is a demo I showed a few years ago where I tried to bring these robots in a conference demo. You can rotate this orange peel, quite unexpected at that time. And then also a few years ago in ICRA, there are audience trying to get random things from their pockets, such as these phone chargers, and then the policy still doing reasonable job. So I think this work that we done during my PhD, and I think simulation is really helpful in making this policy robust and learning complex and agile and adaptive behaviors. So that's one of the reasons I like that and spend most of the time in my PhD. And however, there are also challenges during this process. For example, whenever it comes to training reinforcement learning algorithms, if you have experience, you know that designing the reward is quite complicated, and sometimes it's very, design the reward itself is a very sparse reward process. You sometimes do not know what direction you should work on. And then there are also another problem, which is in simulation, is quite complicated or hard to simulate rich sensings, such as vision, such as realistic high fidelity vision sensings or tactile sensings we want to have in the real world. And there's also a physical level or dynamics level sim to real gap, because simulator is based on our understanding of the physical world. And we inevitably will make assumptions and simplifications of different physical phenomena. So the policy learning simulation is not with respect to the dynamics we have in the real world. So I have recently begun to think about alternative paradigms of dexterous manipulation, and possibly whether we can combining this simulation-based approach with them to achieve better performance or bring best of both worlds to achieve better paradigm of acquiring different skills. So alternative paradigms these days, there are two very popular approaches. The first one is learning from teleoperation data. So this is probably, you see in Twitter, many robotics companies today, they are trying to build their data flywheels and using these approaches. And the idea is that you build a one-to-one copy from your robots to actually from your robots and to some teleoperation devices. And there are some humans who remotely control the robots in a way that the robots directly operate in the real world and collect the sensory motor data during this process. There are good things like there's no embodiment gap because you operate a robot directly in the real world. And there's also disadvantages. One obvious thing is that it's expensive data, but I didn't even list it here because before that, teleoperating dexterous hand is already quite difficult. I'll show one or two videos in the later slides. So it's very hard to get such useful data for robots' hands. And then the alternative paradigm is learning from human data. So human data means when we as a human doing something, we can have cameras, maybe egocentric cameras or some motion capture systems just to record what we are doing. And the idea is that because robot hands and human hands are pretty similar, the similarity in the sense that it's similar to parallel job grippers. So if we can find some algorithms that directly translate human actions to robot actions, then we basically have infinite amount of data to train our algorithms. But there are also problems like when we capture human motions, we cannot get the action labels in this data. We can only capture how human, the key points of human hand, but we cannot observe how much force human is applied during the manipulation process. And in this talk, I'm introducing three of our recent work that basically leverage the advantage of simulation and some part of teleoperation and human data to further advance dexterous manipulation. The first work I want to talk about is called Learning Dexterous Manipulation Skills from Imperfect Simulation. So this is a work going to be appear in ICRA 2026 in 1 month. And the motivation of this paper is trying to see to solve one of the disadvantages I mentioned for teleoperation. So this video is from Northwestern. So actually, I just noticed Kevin is here 1 month ago. And this is their teleoperation system. So you see that there's a human on the back wearing like a fancy glove and trying to teleoperate a very expensive hand to finish some tasks. So this is quite good. So you can doing fine-grained manipulations using relatively easy to control teleoperation setup. But so you might see that we have some way to teleoperating teleoperating multi-finger hands. But another examples they show, although this regarded as a successful example, but you can see if you want to installing this knot on something. So the way they do that, even with 3 times the speed, is still quite inefficient, and it's not as close as what we human can do. And the major reason is that you might notice that they do not have any finger coordinations. They keep using one fingers to doing this manipulation without relying on like using multi fingers in this case. And I think the idea is more profound. So this is another example. So this teleoperator is myself, and I'm trying to do the same task as I showed before. So on the left, we are doing these in-hand manipulations learned by RL policy. On the right, I'm using a very advanced teleoperation suite to teleoperate a pretty good robot hand. So this is a new hand called Sharpa hand. The hardware itself is pretty good. The teleoperation device is co-designed with the company. It has exoskeletons. It also has haptic feedbacks. It does not have haptic feedback, but I'm looking very closely of how it contacts with the between the hand and the objects. But still, it's very hard to teleoperate that. And I think this is because when we use when human doing finger coordinations, we're doing that in an unconscious way. So we didn't notice that how our finger move when we're doing some manipulations. But if we want to do teleoperation, we need to translate our unconscious thinking to a reasoning process. But this translation is usually slow and imperfect. And what appears is that if you directly teleoperating using your reasoning capabilities, then it typically fails. Then how are we going to deal with this issue? How do we enable teleoperation devices to be able to do tasks such as maybe installing a nut bolt or using screwdrivers, which typically requires you doing finger coordinations? And just a recap, I mentioned during my PhD, sim-to-reals give me some benefits, like being able to learn finger coordinations for the in-hand manipulation policy. But it's also, there are disadvantages, such as it's hard to simulate complex sensors, complex scenes, especially if you imagine we want to simulate a nut and bolt, then how many effort you're going to put for these thread structures? Well, using teleoperation, you do not need to build all of these complex structures, but it's also hard to do these finger coordinations. Then the solution of this paper proposed is to using a hybrid or shared autonomy approach that is still rely on teleoperation, but it's a teleoperation over different skills instead of over the roll joint positions of the hand. And there are multiple stages. There are 3 stages of this method. The first stage is pretty straightforward in the sense that we just are training a standard, very typical reinforcement learning algorithms in simulation. This is very standard reinforcement learning loop. You have some observations. You have a neural network policy and output some actions. And we built a very simplified environment to approximate what we have for the nut. So the idea is that you just have a revolute joint and some have 2 rigid bodies connect them. So the upper body can rotate, but it definitely does not have thread structures. It does not have this complexity of simulating nut and bolt. I'll explain why we can do this in a minute. So, and then using standard algorithms such as PPO, proximal policy optimizations, you can learn reasonable behaviors using this hand on these simplified environments. And of course, during this process, I made a few assumptions, which is incorrect. The first one is, for example, the physics is imperfect. And so for example, I use these simulated nut bolt structures to approximate what we are going to have in the real world. And we also have limited sensing modalities, such as in this process, we do not consider simulating tactile sensings like in the simulation. Then we get some policy, but this policy may not be directly applicable or autonomous in the real world. And the solution is that we are going to, instead of treating this as a final autonomous policy, we treat it as a scaffold for our data collection process. And the idea is what we show on the right. So we have a human teleoperator. The teleoperator, instead of, as you see in the previous video, trying to control each individual fingers, it only tries to, the human only tries to teleoperate two things. The first thing is how the arm is moved, how the arm moves. And the second thing is whether this RL policy is activate or deactivate. And then and the activation is passed to a RL policy, and the RL policy is going to output the finger joint positions. And in this case, we have two advantages. The first one is we can delegate the fine-grained finger motions to the policy. So the human does not need to worry about the finger coordination part. And the other thing is, because this is in the real-world data collection, we can collect rich data such as real-world proprioceptions or real-world tactile data into a new data set. And this data set is, because it's collected by the teleoperation, there is also bridge the physical gap. So previously, although the policy is trained with simplified object dynamics, but when you're doing real-world data collection, this environment is completely adapted to our new environments, like the nut bolt is the correct thread structures. And this is what it looks like when a human teleoperating the hand. So there are two things you can notice in this case. The first one is the human can have a much simplified interface to control the robot instead of wearing a heavy and glove. So it can only use like Quest controllers using a few buttons to control this hand. The second thing is the policy itself is indeed not perfect. So as you can see, sometimes it is kind of get blocked during this rollout policy process. Typically, if this is autonomous policy, it will just stop there. But because we have a human, we can keep adjusting whether this policy is activate, and then we can also adjust the arm. These human corrections help the policy doing some like explorations during rollout, so that it can succeed during this nut bolt installation process. And the good thing, as I mentioned, is that after you have this real-world data set, you can just apply your favorite behavior cloning algorithms and to learn from this data set to get a behavior cloning policy. And this part is this part we just apply the standard ACT algorithms in this case, and this is our final policy we get. It's an autonomous rollout in this case. So in this paper, we have not used vision as the input. So the policy only relies on tactile informations and proprioceptions to finish this task. And one of the advantages of relying on tactile instead of relying on vision is that it's pretty robust or generalizable according to over different visual appearance. Because although these two nuts are quite different, but their local contact signals between the nut and the fingers can be quite similar. This is another example of me applying the same policy trained before and applying a new nut here. And another interesting phenomenon is that what's the usage of tactile in this case? So for example, using tactile, you can infer what's your relative positions between your fingertips and the nut, so that the arm can slowly, gradually going down when trying to installing the nut. Well, if you do not have tactile, although you can still rotate the nuts for several certain revolutions, but after the nut is going down, there's no way that the policy can tell is going to, to tell the relative positions of the nut so that it cannot going down and finally fail.
I have a quick question. So during the real rollout of the autonomous policy, does the policy also output the whisk motion collected by the human operator?
Yes, it outputs both the finger and wrist.
So in the simulation, the policy also randomized the rotation, so it can like rotate things or.
It has certain degree of rotations, but mostly it comes from the behavior cloning stage, because when human collects the data, human control the arm motion, and this arm motion is recorded, and your policy observes this kind of motions.
Okay, got it. Thank you.
And we can also apply similar pipeline. So this is not the same policy, but the pipeline is similar for this screw driving task. And it's also quite robust. So I should having a 2-minute video of this, but it can. So in this project website of this paper showing a zoom-in version that shows the screw is actually correctly installed. A summary of this paper is that we can use simulation to help us learn very complicated and reactive and short horizon skills. And then combine it with human teleoperations, it will require less tuning due to human online corrections. So this relaxes a lot of effort of tuning domain randomization parameters or trying to do like sim to real alignment. And then after we get these 2 steps, it can be easier to collect real world data that previously you cannot collect using typical like maybe motion glove or retargeting type of method. Any questions? Okay, then maybe I'll go to the second work. The second work is called Spider. It's a scalable physics-informed dexterous retargeting. And in this paper, we are trying to deal with the problem that given you have a human motion, it can be from some data sets, it can be from like mocap or YouTube videos. How can you translate this human motion to a robot actions? Why we are interested in this? Because like human data is great. I think especially this year, if you go to Twitter, there are every day a lot of robot companies trying to say we are collecting human data and this is important. This is indeed good in terms of is quite abundant and is easy to collect at scale compared to teleoperation. You just probably need cameras on your head and then trying to hire some people use their own hands to do tasks. And there is also, it's easy to collect a lot of diversified tasks, such as like all the daily tasks you can basically doing in this way, asking so many people in their daily lives. And it's also another story we want to tell is that it's naturally aligned with robot hands. And also, but however, although there are many different advantages, it's also quite challenging if you want to use it directly for policy learning. And the two major disadvantages is that, firstly, if we capture the human data in this way, it does not have action labels, and also it does not have dynamic informations. And this is because every time step when you capture this scene, you can only get the state information of your hand and objects can be noisy, but it's also do not guarantee that you do not capture the physics of the whole manipulation task. It also have embodiment task, definitely, because no matter how advanced is our robot hands, it's still quite different from our human hands. Then a typical pipeline in this field is that given a human video showing on the left, we are going to apply certain computer vision algorithms, such as maybe hammer to detect the hand pose. We also get some post-estimation method to get the object pose. And then we process that frame by frame, and then we can get a trajectory of 3D informations, such as in the middle, this is a 3D trajectory of hand, objects, and doing these interactions. And then what we could do is usually doing what we call kinematic retargeting. And the idea is that we want to translate human hands to a robot hands that we are interested in. For example, this is a legal hand we try to map. And this is usually solving some optimization task, saying your human hand fingertips should as close sorry, it should be the other way. So your robot hand fingertip should match as close as the human fingertip. And then you get a new trajectory that is on the robot hand instead of human hands. But there are obviously some problems. So in this case, none of this method considering physics. So if you look carefully during this process, sometimes there are some penetrations. Sometimes there is also like weird physics, and sometimes the trajectory path is also not even smooth. Then this is definitely not able to train a policy using this method. So the idea of the second paper is basically using simulation as a tool to make the retargeting pipeline physically plausible. And the idea is quite straightforward, I would say. So in the previous slides I present, after we get a retargeted trajectories, like the robot motions and the object motions, we are going to put these trajectories in a simulation. And then in this simulation, at every time step, we are going to sample a lot of random actions around these reference trajectories. So if you know about maybe sampling-based method, sampling-based MPC, you can consider we have these retargeted trajectories. We are going to sample a region around these trajectories, and because this is in simulation, we can run the simulators for each of the trajectories, and then check which one is the most close to our desired object trajectories. So one conceptual visualization is that when you're running this method, each of the curves on this video showing one of different hypotheses at each time step. For example, this is the fingertip possible locations in this current time step. And we are going to, as I said, run the simulation and then check in each of the trajectories how the object will behave. So if the object is with respect to the reference trajectories, we are going to choose that frame. And this process is iterated over many steps. And then after the whole episode is processed, we can get these desired action trajectories. So there are two advantages of this post-processing pipeline. The first one is that after you run this in simulation, you can guarantee that your trajectory is physically plausible, in the sense that it's plausible with respect to the simulation physics, although it's maybe not accurate in the real world physics. But on the other way, we can also get a trajectory of actions instead of trajectory of state, because the difference is that instead of, in addition to the current positions of your hand, you also know what is the hand next. You also know the next state or the next desired state of your action, so that you implicitly know how much force your robot should apply. And this method is general in the sense that as long as you have an object mesh and it's relative accurate, as long as you have a relative correct reference trajectories, you can easily doing it for multiple hands and even for the humanoid. There are some tuning of the hyperparameters of MPC for each of the data set, but after you tuning that, you can basically run it for the whole data set, and the process is quite fast compared to previous this type of post-processing methods. And one of the tests of whether this action is physically plausible and whether this action is good is that you can directly run these trajectories in the real world in an open loop way. So here are some videos I think we run in the real world. So in each of the videos, you have a reference trajectories showing on the corner. And then we basically first using this typical pipeline of converting that to a kinematic trajectories, and then using our method to refine that to be physical plausible, and then doing the sim to real transfer. And then, so for each of them, just one thing I want to emphasize is that the success rate of this deployment is not going to be high because this is open loop trajectories, and this is open loop trajectory does not have sensory feedback or error correction online. But the fact that it can success sometimes, meaning that their trajectory, the quality of the trajectory is much higher than previously what we can get. And previously, if we directly doing kinematic retargeting, none of them can be successful. And another thing that we can test whether this trajectory is getting better is to use these trajectories as a reference for downstream RL training. And the purpose of that is we want to turn that into a sensory motor policy instead of just the open loop. And as you can see, if you directly doing kinematic reference, so sometimes because it's not physically plausible, and then RL training is much more difficult compared to after you're doing a good reference trajectories. So this is, similar observations with respect to the humanoid research community, where they found the quality of your reference trajectories can be significantly affect the policy performance. And in this case, we just show if we refine the humanoid trajectories, the task progress can be significantly higher compared to without polishing that. And to summarize, in this work, we can use a sampling-based method to generate feasible trajectories in simulation. These trajectories are already, it's good and executable. So that's why they can be replayed in an open loop reliably. However, they currently lack sensory motor feedback, limiting robustness and adaptivity. There's no online corrections, and there's no robustness to initial object state estimation errors. And it can also not react to changes during your replay process. Any questions for this part?
What do you think was the biggest challenge when to bridge the embodiment gap, like either from the human demonstration to the robot to the real robot demonstration, or from like in the wild demonstration lab robot data?
Just to make sure I understand, you mean what's the biggest bottleneck right now?
Yeah, like challenges or using issue. It would be like the hard blocker between the process.
I see. I think there are two major blockers. The first one is, let's say you want to have in the wild, like the most general way of translating human robots to, like human video to robot actions. Then I think in this case, the biggest bottleneck is the computer vision part. Because in the wild, very accurate human pose and object pose estimation is still very challenging. Like in most of the cases, I would say. So some of the video I showed, the human video is in a structured environments. So there are even mocap data or other settings. So it can capture very robust 3D models or pose during this trajectory. But that's not true for in the wild video. And let's say on another case, that is, we have a structured or instrumented environment that we solve the vision part of our problem. Then I think in this case, it's more like the the pipeline of, I mean, I still believe, I believe this pipeline of translating, I believe the pipeline of translating kinematic trajectory to dynamic aware trajectories. But I think the bottleneck is that, so firstly, the tuning process of the trajectory is still quite tedious and it requires human effort. And then it also needs a relatively large effort to select which reference trajectory is good or not. Because sometimes, maybe this is too deep details, but I think sometimes even though you get the state estimation correct, but when you import to a simulator, penetration can happen. And there's some like unstable physical solver can happen. So there are many cases like the optimization process just fail as a first step. And we need to spend a lot of human effort in this case. And if we need to spend human effort on many cases, so this method itself cannot be very scalable. Okay, then I'll go to the third part, the third work, which is called OSMO, open source tactile glove for human to robot skill transfer. And the idea is similar to the previous work. So we want to have a human video, we want to translate that to a robot deployment, robot actions. Previously, I used simulation as a way to provide action information, so dynamics informations. But this way, this work is an alternative way of how do we provide these informations during human video collection. The idea, I mean, the motivation is kind of similar, that we have lots of human videos, but this is vision only. What if we can collect some tactile data? And the good thing is that the tactile data could recover action relevant signals. It can also get rid of some kind of simulation challenges we just mentioned. Then so if we have such a data set, it will be much easier for us to learn policies. But of course, the challenge is that our internet scale data sets are vision only. We do not have such a large tactile data set. In all of these data sets, we do not have direct tactile or force informations. And more arguably is that this also means many of the fine-grained interactions that is critical for manipulation. So before I present the work, maybe we can think about what may be the key characteristics of such a tactile data set. So if we have such a data set, what's it useful and what's the requirement for this data set? So I think firstly, this data set should capture unconstrained human dexterity. So because if you do not have that, there's no point of, because our goal is to achieve human level dexterity. If you do not capture that, if you sacrifice that, you may miss our final point. And another thing is that we wanted to record comprehensive shear and normal forces. We need some richness of the policy so that we can fully leverage the tactile sensing. And ideally, we also wanted to provide full hand coverage. We wanted to cover the palms, the fingertips, so that this is a basic requirement of our, if we want the robots doing our daily tasks. And another thing, which is very closely to what I just presented, it should be integrated very smoothly with the off-the-shelf hand tracking method. Because, well, otherwise we cannot get hand pose, we cannot easily get hand pose. And then a nice property that we have is if we can have the identical sensors for both human data collections and robot deployment, then we can minimize the gap between the data collection and the policy rollout. Otherwise, you need to do like infinite amounts of sensor calibrations and alignments. Then that's a very painful and also inaccurate process. Then holding this wish list as like in our mind, we developed this OSMO Glove. So this is currently open source tactile glove that we can use to study human to robot transfer. And the idea is that so as you can see, this is a human wearing this glove, and the glove is kind of thin. I guess when I wear that, it will definitely, the wearability is pretty comfortable, and I can use it to do any task I can do. So compared to a typical glove, it just adds a few magnetic-based tactile sensors. There are, I think, 12 of these sensors. Each of them is based on some previous work, either called, so it's a long series of work from Reskin in Meta or Anyskin from NYU. And the idea is that you have this skin that is built from magnetic elastomers and also magnetometers, so that whenever you press the upper magnetic elastomer, the magnetic field will change. And then your PCB board will also sense that effect. For example, when you press it here, so there are different PCBs, and each of them give different each of them gives you different response. So although there are only 5 sensor units, but you can interpolate them and get a very fine-grained sensor signals. So to verify some of our previous wish lists, and especially the off-the-shelf vision-based method to get human pose, we wear the glove to try to use different methods to get the hand pose. And this is part of the reason why we designed the color to be this. Sometimes to be cool, you want the glove to be black or white. But we found that if the color is black or white, you cannot use traditional method. You cannot use vision-based method to detect the key points. But if you use this color, you can use either different area glasses or hammer or maybe Apple Vision Pro or Quest 2 to get a pretty reliable human pose. So this can also be combined with Manus glove, just by after wearing this glove, you wear another Manus glove, which is reduce the variability, but it's also useful to get a super accurate human hand pose. Another thing is that what we can get is the quite rich shear force sensings. So here is like a slow down video trying to capture what the sensor can sense when the human open a cap. I will play it again. So it shows the middle finger tactile skin tight. And as you can see, there is a sudden jump when the human applies the red force. And then this is a good way to detect the event from this tactile signal. And here is another example to showing how the signal will behave during this process. But note that the signal here is not physically meaningful because it does not directly measure force, but it only measures the magnetic flux, which is some magnetic terminologies to see the response. But the relative changes are pretty consistent and calibrated. And of course, for roboticists, our final goal is trying to collect data using this glove. So here is a video showing human wearing this glove to collect these wiping videos and the corresponding XYZ like three-directional forces during this process. Another very good aspect of this hand is that we designed the hand such that it can be worn simultaneously by a human and a robot. If you have a small enough robot hand, which currently we do have a bunch of these options. So as you can see, if this glove is worn by a human or worn by a robot, visually it's pretty similar. And also, of course, the tactile signal is also consistent because that's the same glove you used for data collection and policy executions. And we use like off-the-shelf diffusion policy to get to training the behavior cloning so this is basically using human to collect maybe 200 trajectories, which is pretty efficient in our case. And then trying to deploy a robot policy on wiping this on this wiping task. The robot experiment itself is not super impressive, but I think it basically verifies the concept of you have a glove as the interface that can minimize the tactile sensor gap as well as the visual gap between data collection and deployment. Finally, to summarize this project, so we developed this open source tactile glove that that you can directly download it online. So it requires some effort to assemble it, but I think it's a pretty useful thing to if you are interested in this area of research. And it has some way to minimize the visual and tactile gap. And it's also compatible with the existing human to robot pipeline so that you can directly apply your human hand pose estimation and retargeting methods in this process. And to recap, I introduced 3 different works that the first 2 sort of combine simulation with other paradigm of skill acquisition. So to achieve better performance or solve some kind of problems of different pipelines. And on the third one is a hardware level innovation that we can use to make human to robot transfer better. Yeah, and I think in the future, so this can be further kind of integrated. For example, after you can collect the tactile signals, you can use this as additional guidance for your simulation policy during your simulation policy training, and then get better performance, of course. Okay, I think I'm almost on time. Then I'll say thank you for inviting me and happy to answer any questions.
If you guys have any questions, feel free to ask.
I have a simple question. Do you think your third project can combine with the first one because the tactical sense of speed rank can make the first one more accuracy and can train more better for the robotic hand?
Yeah, I think it can be definitely combined. So, well, one way you can consider combine is provide additional reference to your RL policy training. So human doing this NAT installation, and then you get the human trajectories. You also get the force, and then this is this is a reference for your RL training. Next questions?
It's interesting that having sensory feedback seems like a very good thing to have as an additional reference point. Or
sorry, I might not hear it clearly. Can you say it again?
I was saying like having like sensory feedback, robotic arms, hands seems like a very useful reference point for them. I just was wondering what do you think that it's not more common in research?
I see. So I think the question is why this is not commonly adapted.
Yes.
Like in all projects. Well, I guess the hardware itself, I would say, is not that mature in the sense that, let's say you want to buy a camera, you can order it, and then you can use it for months or years. But for this type of tactile sensors, you need to make it. Like you cannot order off the shelf. That's already a huge bottleneck. And also the difference between tactile sensors and camera is that tactile sensors, you always contact something. And then there are various tiers of the sensors. It can usually be used like days or weeks, like in this level. And also because it's not standardized, or because it's you need to make it by yourself, different sensors is also inconsistent. So whenever you change a sensor, it also brings a problem of calibrations or different things. So I think that's like why people are not using tactile sensors yet.
Yeah, I also have a question. So basically, I think hardware is it's very challenging when you deploy your robot. So I feel like there are a lot of sensors, like the traditional magnetic sensor, there are a lot of crosstalk issue. And the vision-based sensor, you collect, I mean, if you collect a large amount of data, your gel, you might be replace it. So how do you think about the tactile sensor, the hardware itself? What kind of sensor is good for the learning?
I think honestly, so firstly, I'm not a like robotics hardware expert. But I closely observe this field. I think it's pretty, I mean, recently it's very having a lot of great progress. So for example, from reskin to AnySkin, I think the crosstalk issues has been not AnySkin, but from reskin and AnySkin to the next version of AnySkin. So the crosstalk issue has been largely reduced by introducing a magnetic shield mechanisms. So in our case, we also have a magnetic shield. Otherwise, the crosstalk will just be too large and you cannot learn anything meaningful. For vision-based tactile sensors, that's always you have this problem. But recently, for example, Sharpa's vision-based tactile sensors, I think this pretty I would say it's not, it's at least maybe 10 times robust than maybe gel side. So I think the technique can be made much more better if there are more people working on this and then more maybe funding or interest towards this field. So I think I would see it has a bright future and is evolving quickly. Yeah.
Thank you.
Yeah, questions.
So if you want to learn from people's video on YouTube, but there is not include the sensors data like the force or something, you want to finish some contact reach tasks. So how do you deal with it?
I think I can answer it in like two folds. The first one is the reason we want to have tactile data is because we do not have this data online. And then we think if we just learning purely from vision egocentric data, it will be very hard to get contact reach task working. Yeah, so that's one way to answer. And the second way is basically another way to think about this problem is you can having some like initial policy or initial model that is vision only, and then after that you have a data set, still have large amount of data, but maybe smaller compared to internet scale data. And then in this case, you can fine-tune your models using certain mechanisms, and then getting this policy to take additional tactile inputs. Yeah.
NPC to turn in the parameters or like so like how do you do some like decoupling or like combine the inputs efforts?
I see. So we do not use the MPC to tune the parameter. I would say we use MPC to find the optimal action, but we need to tune the parameters for the MPC, such as what is the horizon length, and then what is the noise scheduling, what is the range of noise to get this action sequence.
You need like the recurve one or like backend?
So this one is particularly called Del MPC. It's the first author's previous publication. It's a like typical MPPI plus a special annealing procedure to sample the noise. Yeah.
Well, using the human demonstration, do you think, because there are plenty of like on YouTube or like online, there are many like human egocentric videos. So do you think they can be directly used as a data set, or we should use the human demonstration to, like, we should collect the human demonstration on our own to be like, to reach some specific task or specific requirement to be more intuitive or easier for robotic like learn?
I think the difference between these two sources is their quality. So I think for now, these YouTube videos, maybe they are good for pre-training, but their quality is not enough to directly learn a robot policy. So I would say, depending on if you want to study pre-training or want to study how do you directly learn policy from human data, then the requirement will be different. So if you are interested in directly getting a policy from human data, maybe collect by yourself, although the amount is smaller, the number of trajectories is smaller, but the quality can be much higher than in the wild videos.
Any question?
Yeah, so I have a question about your first work. So I think I really like the idea of using some like short horizon primitive. And I'm curious, how do you think it could scale to more complex tasks that requires like other primitives? And what are those primitives?
So more complex task, do you mean like maybe longer horizon that requires several skills?
It can be more longer horizon, can also be tasks that require the use of other primitives than the access.
I see. Let me see. So I think that's a good question. So that's I have a list of skills that I think is pretty important, and maybe the number is like 20 or 30 skills. And these skills is decided by it's not decided by semantic, but maybe decided by the contact modes. So for example, let me think. So for example, in this work, typically people can think both not task and also screwdriving task is different, but essentially their low-level motor skills is in-hand rotation. And other examples including maybe if you want to cutting vegetables or cutting meat, this can be also unified one skill. So I'm thinking maybe if you are using tools and you control the tools in certain ways, defined by the contact mode, they can be unified one skill. And so going back to your question, so I think I would imagine, so let's say when we deal with a new task, then I believe that the new task can be always decomposed to several subsequent tasks. For example, if you have pick and place, if you have in-hand manipulations, if you have the ability to control a tool in certain ways, you can already finish a huge amount of different tasks. And the number of sub-skills are not too many. So I think maybe even for a long horizon task, you can utilize less than 5 skills. And on another task, maybe 5 different skills. But for a task itself, you can just win control over 5 specific skills. And so it would be, I think it would still be feasible to have an interface such as a controller, a quest controller, or some maybe controller having different buttons to switch between different skills. On the other hand, the number of skills, maybe I can share the list offline, but basically it involves maybe wiping and cutting and insertion, and also I think screwdriving is one, and also pick and place. I think I listed maybe after 20 of them, and then after that I realized maybe in our daily life, this can already cover 90% of things we are interested in.
That's very interesting. So it's like coarse motion skill and fine motion skills.
Yeah.
Any question? Okay, thanks, Haozhi, again.